Hello everyone and welcome to this solution video of the day 3 challenge that we launched for Edyst 2021 June daily challenges, and also a special announcement about the algorithms and data structures bootcamp that we are launching. So let me first begin by that special announcement. The special announcement is that we are just 1 week away from the algos and data structures bootcamp launching, and we've run successful batches earlier. We've had great results. So what do we actually cover in this batch? A lot of you are asking. Well, we cover about all of the important concepts like arrays, strings, dynamic programming, backtracking, data structures, graphs, all of it. For a detailed syllabus, you can check out the link in the description below. What you can also expect is personal time with both me and Devang. So we are instructors for this course, and we have helped a lot of students crack their dream product companies. Some of the product companies that we've helped them crack, you can check in the logos over here. So our students have cracked companies like Google, Adobe, JP Morgan, Flipkart, DBS, Amazon, ServiceNow, Twilio, Zenoti, all ranging from 10 to 45 lakhs per annum. Yes, you heard it right. And if you've been enjoying doing the daily challenges, if you felt that I can do these challenges, it's a little bit difficult, but I can understand the concept, then for you, these bootcamp is the best thing, because you already have some coding knowledge and we can help you actually crack the best of the product companies. So you can check out the link in the description below. It's not a free bootcamp, obviously. It is a paid bootcamp, and we have the option of you can do the entire thing at once, or you can pay it in installments. The fees is just 6,500 rupees, and you can also do that in installments. So all of that, details are in the description below. But yeah, it's roughly a 2.5 months bootcamp where you will get in-depth mentorship from us, and also you will get more than 300 questions where you can actually practice and prepare for all of the product based companies. So don't lose out this opportunity. We are selecting only 30 students for this. It's a very selective batch. We are not going to select everybody, so it's a pretty selective batch over here. So do go ahead, apply. The seats close in soon, so please do that. So now we'll move on to the day 3 solution that we were talking about. And for those of you who don't know, this is day 3 of our 4-day daily challenge. From that started on 8th June and is going up till 11th June. The first to crack the challenge will be on the top of the leaderboard and actually also wins the prize. So those people who have not yet signed up, please check out the link in the description. You can sign up for this as well. Coming to what are the prizes, well, we have this unique thing with that we're giving out 2 prizes. One is the daily winner gets 1 prize, and one random participant also ends up getting a prize. So today's winner, that is the day 3's winner, is Raghavendra, and he's won an MI Smart Band. So congratulations to you, Raghavendra, for winning an MI Smart Band, and Suprita for winning JBL headphones. So Suprita is a random winner for today. What do I mean by random winner? Suprita has just come and attempted the question. That's what a random winner is. Did they solve the question? Did they not? I'm pretty sure she solved it later on, but she's won a JBL headphones right now, just for participating. So everybody, we still have some challenges. Do participate and win your own prize as well. So that's what you can expect. Now let's actually go to the question and the solution of the question, right? So let's look at this question over here. So yeah, this is the question. Socrates is located at the top left corner of an n, grid. And it has some obstacles. In one move, it can move any number of squares to the right, downwards, or diagonally to lower right. This is the trick of this question in the first sentence itself, that it says that you can move any number of squares to the right, downwards, or diagonally to lower right. Any numbers. Usually you have seen this kind of a question in which you go one move to the right, one move to the left, and so on. So this is the first issue. Now obviously you cannot move to an obstacle. There is something called an obstacle as well. So if I read the input over here, what I get to see is there are dots and there are hashes. The hash over here is an obstacle. So I can't move over an obstacle. I can move directly to the next, or I can go to any particular point, but if there's an obstacle in the way, then I can't really go over that. Fairly standard. What I need to do is, I have to count the number of ways that I can reach from the top 1 to the bottom n cross m. So from the top of a grid to the bottom, how can I move? To the top right, or sorry, the top left to the bottom right, how can I actually move is what I need to do, and I have to count it modulo 10 raised to 9 plus 7. All right. Now, the first things first is, if you have not seen such a question before, please know that this is a very standard question when it comes to algos and data structures. This pattern of question, I'm not saying this question particularly, but this pattern of question. And what happens is that you get repeated patterns in every algos data structures questions. You always get repeated patterns. You'll get a similar question and you're supposed to figure out, okay, how does this map to a pattern I have seen earlier. The trick in algos data structures is to be exposed to as many such patterns as possible, so that when you get a question, it doesn't seem like a new question. Even the people who solved it yesterday, this question, day number 3, would also realize that this is a question that they've seen earlier. It's just with a twist. And that's what you have to get good at. Number 1, identifying the pattern, and then 2, identifying the twist. So the pattern, if you had already identified, is that how can I figure out from a particular point, how do I move to the next point? Okay. And so we'll actually look at that. We'll look at the easier problem first. Okay. The easier problem is that if we can only move one unit at a time, not any number of units we want. Okay. And some of you might be new here. You might still not be able to understand this part. So let me just show you how that works out. The easier problem here would be something like this, where let's say I'm at this position 1 and assume there are no obstacles. Okay. If I wanted to figure out how many ways are there to reach this position over here, I would simply say how many ever are the ways of reaching, this position. It's, the number of ways of reaching this position is equal to the number of ways I can reach this position over here. And that's actually correct. I can move left and left. That's the only way, or right and right. That's the only way that I can actually move. I can't move further than that, right? So if I had to show you how to reach here, I would say, okay, you are here. This is just one right move. This is 2 right moves. Okay. And this is 3 right moves, which means that there's only one way of reaching here. Now you'll say, sir, I am doing 3 moves here. How are you saying there's one way? No, the moves are 3, but the move sequence is only 1. So just to show you again, let's say if I'm here, I can reach here only in one way. That is, from this position, I'll come down. However, here I can reach in 2 ways. I can come here, or I could do RD. What does that mean? From here, I could move right and down and come here, or I could move down and right and come here. Okay. Or I could actually move diagonally as well. So what will be called diagonally? Let's just assume a word called X to use diagonally. Or I could have just done X as well. So actually there are 3 ways of reaching here. I could from 0, 0 or 1, 1, whatever you want to call it. From here, I can move here in 1 step. I could have gone down and moved to the right. I could have gone right and moved down. Okay. Here I have 3 ways of coming over here. All right. What about here? Again, I could have moved diagonally over here. I could have come from above, or I could have come from the right side. Now, if I had come diagonally, it would have just been Rx, right? So Rx, how Rx? There was from this position, I moved R over here and then X over here. All right. Now, again, I'm saying that I can move only once at a time, right? So I'm saying, okay, Rx. Here, I could have come down. So I'll say, okay, this also is a possibility, RRD. And all of these ways, I could have just said move right. Okay. So I could have just said, okay, for DRR is one way, because I'll do DR mix, and let me just increase the space here. All right. So I could come here DRR. I could also do RDR, and I could also do XR, right? XR, but R means move one position to the right, down means move one position down, and X means move diagonally diagonally down. Okay, so that's what we're doing. So overall over here, how many ways are there of reaching this position? There is 1, 2, 3, 4, 5 ways. How did we get these 5 ways? If you think about it, it's because all of the ways on the top right, or the top left over here will lead us here. That means all of the ways of this plus all of the ways of this plus all of the ways of this will help us figure out how many ways are there that I can arrive at my current cell. Okay. So instead of all looking at it like this, I generally like to look at this question or any such question as think of the regular case, the usual case. Okay. Think of a particular usual case. What is that usual case? Let's say any cell. Let me pick up this cell over here. Okay. And for this cell, how many ways are there that I can arrive at this cell? Well, I could arrive at this cell from here. Okay. So I can arrive from here, from the left side. Let's say I could arrive from the left side. I could arrive from the diagonally top side. So this is another way of coming here. So let me call it as X, let's say, and this is from the top is what I can come, right? So I can come from here as well, and probably let me call this as T, the top, right? I could come from any one of these places, right? Let me just take a better color. Okay, so let me just say, like, from the left side, from diagonal side, right, and from the top. In all of these come to my yellow square, to my yellow cell, I could have come from here, or from here. If I'm allowed only one move at a time, again, I'm solving the easier problem first. And so the recurrence relation, or the relation to figure out how many ways are there to come here, is quite simple. I can just say how many ever were the ways of reaching diagonal, how many ever ways were there diagonal, plus left plus top. So what this translates into is that something like this, where the easier problem is that I can say that number of ways of reaching I comma j is I could have appended a character to any of the ways from my previous column. So I could have just moved right. So I say ways I minus 1 j, ways I j minus 1. This is coming from the previous column, or I'm just making a right move. Plus I could have come from the above row, so it will be I minus 1 j. Okay, so same column but above. So how many ever are the ways of reaching above, those same ways translate to helping me reach here as well, plus the number of ways it was in reaching the previous row and column. Why this? Because I have to come diagonally. So I minus 1 j minus 1 will give me the diagonally. This is the case if I could move only one element at a time, and I can figure out how many are the ways of reaching. And you could technically, I think in Google Sheets this is pretty easy to do, but anyways, I'll just skip that part. But my point is, this is the recurrence relation that forms with the initial thing that you will say that, okay, ways of 0 comma 0 is equal to 1. So you'll say that, okay, I'm already here, there's one way of reaching here because I'm starting at this point, and everything else starts following from here. So you start kind of building this cell over there, or the grids over there. Now the issue is, this is not our question. Our question says we can move any number of moves. So if I go back to our grid, and here when we were talking about, no, I can't, here what we are saying is I could have come from here, here, right? But in our question, the Socrates travel question, that's not what we are told. What we are told is that if, again, we'll take up this yellow cell only, okay, but we are saying that, okay, these are not the only ways that you could come from. And so just give me 1 second. Yeah, these are not the only places that you could come from. If you were to arrive at this place, what you could come from is any of these, that is any of these ones you could have come from, because as I said, we can move any number of elements to the left at any point, any number of elements diagonally, as well as any number of elements to the below as well, right? So we could do any number of these. So I could have moved from any of these cells, right? Any of these cells would have allowed me to come. Any of these cells also would have helped me to jump to my current thing. Any of these ones. So, let me put that another color here. And any of these cells would have also allowed me to jump to my particular cell, which would come out as this, right? So any of these green, these purple or blue cells help me reach my yellow cell. All right. Now what I finally need to do is I need to calculate the number of ways of reaching here is the number of ways of reaching here plus number of ways of reaching here plus number of ways plus. Why? Any one of those can help me jump forward. Any one of those can actually help me jump forward over here. Okay. Similarly, over here will be number of ways of this, number of ways of this, number of ways of this, number of ways of this. Any one of these can help me jump forward here. Similarly, number of ways here, number of ways here, number of ways here, and number of ways here will help me jump forward. Okay. If I add all of those, I'll come forward. Now there is one small caveat here, or one small exception, that if any one of these is an obstacle, so let's say for example, if this was an obstacle on its own, if this was an obstacle, or let's say this was an obstacle, then you cannot jump from here till here. There's no way that you can jump from here till here. You can jump from here and here to this position, but I cannot jump from this position. That is, 1 second. Yeah, this position becomes invalid now. Okay, that is your 3 comma 0 becomes invalid. Your 7 comma 0 and 7 comma 1 also become invalid, because from there also you can no longer jump to my yellow position. So whatever relation we do, we need to figure out how many are the ways that are there of reaching this position. Okay, or this position, but keeping in account that I could also come across some obstacles. All right. Okay. Now let's go with a little bit more. Let's go with the simplest approach here. The simplest approach would be for each cell. So let's say for this cell, what I'll do is I'll keep going up and calculating how many are the ways of reaching the previous ones. So for this one, I'll keep going up and calculating how many are the ways of reaching previous one till I encounter an obstacle. Here I didn't have any obstacle, so I summed up all of the ways above. Okay. Here I'll sum up this and this, but I'll not sum up beyond that orange because there's an obstacle. So I'll just stop there. I'll not sum up beyond that. Similarly, here I'll just sum up this blue, but I'll not sum up beyond the orange because those are my obstacles, right? So I can't really reach I can't jump over the obstacle. It's mentioned in the question. So one of the ways of doing this is for each cell, traverse all the way up, traverse all the way diagonally, traverse all the way to the left side, and figure out the sum of all of the ways of reaching over here. Now, as you will see, and we will also check, the constraints are not really satisfying or doesn't really help us out with that. Okay, n and m are up to 1000 and 1000. So you could actually have in this entire list, this entire thing could be 1000 by 1000, which is 10 raised to 6. 10 raised to 6 meaning 1 million, which means that I can only go through this entire 2D array once. I can't go through it again and again. Why? Because as I've said earlier, that 10 raised to 6 is usually the maximum, or the order of 10 raised to 6 is the maximum computations you're allowed. You're not allowed more than that. So had I, for example, if I've here, let's say this is the 1 millionth one, what I am talking to you is go and take sum of all of these till here, which will be what? Which will be 10 raised to 6 over here possibility, here also 10 raised to 6 possibly, and here also another 10 raised to 6 possibly, right? Whatever is the diagonal, how many diagonals will we have? Yeah, I think roughly that many only, but that's the point. So 10 raised to 6, 10 raised to 6. So what we are saying is for each element, that also, by the way, for each element, we are trying to do an n square thing. So for this element, we will do as many as there are rows, as many as there are columns, and as many as there are diagonals. I am going to do the computation, which will cause us a problem because that will be order n square. We need to think one step forward. What we need to think over here is how can we store already. So again, let's take one step forward over here. This one will work, by the way, if you are just summing up all of these. This will work for some of your test cases. Do try it out. For some test cases this will work, but now I'm talking about the optimal approach. So the optimal approach is as follows. Okay, it's kind of like this, where what I'm trying to do is I'll again probably remove these. Hold on, or we'll make them all, let's not assume any obstacles for now. Let's understand what we're trying to say here first. What we are going to store in every cell is not just the number of ways to reach our cell, but the number of ways of reaching or number of ways of summing up from the left side. Similarly, number of ways of summing up from top and number of ways of summing from the diagonal. You'll be confused. You say, what does this mean? No, this means that I will at this point, okay, at this point, what I would have done is taken, or for each cell, let's talk about at each cell, I'm going to store 3 components. Let me call that as sum left, okay, sum top, and let me store that here actually. Sum left, sum top, and sum diagonal. I'll store this sum also. Hold on. Sum top and sum diagonal. Why will I store this sum also? So that when I'm generating the next sum, I don't have to take all of the sums again. Okay, think about it. We'll come to this in just a second. So let's say even this has the sum top, even this has that, and even this has it. Okay, so what's going to happen now is, let's say, yeah. So hold on, just formatting it a little bit better, guys. So just give me 1 second. Yeah. So let's say I'm talking about this yellow for now, for this yellow cell. Okay. What I'm going to do is I'm going to take the sum left from here. Okay. So I'll take sum left of previous column. Why? Because it's only from here that I can actually jump, make a left turn, right? Or probably make a right thing, but I can only horizontally, I can move only from here. I cannot make a left. If I make a right turn here, or basically go forward in the right direction here, I will end up here. But if I want to end up here, I would have probably taken a right step from the previous one, 7,3. For me to have come from 7,3, it means all the ways there are of reaching the left over here. Okay, all the ways there are of arriving, or what it means to say is sum left is going to store all of the ways of reaching each of these elements. Sum left is going to store all of the ways of reaching these elements over here. Okay, Some diagonal is going to store all of the ways. So this diagonal for this blue is going to store all the ways of reaching from this diagonals over here. But that's not what we want. What we want is sum left of the previous column, sum diagonal of the previous diagonal, okay, plus, so this should be sum left of the previous column plus sum left of sum diagonal of this plus sum top of previous row. Okay, what does this mean? The sum top has stored the sum of all of the elements so far. The sum top here has stored the sum of all of the elements here so far, that is the sum needed to reach this particular element. Similarly, sum left here has stored all of the sums of reaching till here. When I say sum left, I'm talking about this blue one. Sum left is taking a cumulative sum of summing up from the left all the way here. Similarly, sum diagonal is taking a cumulative sum of these diagonals so far. So whenever I generate a new answer, like say for example I want to find this, I will take the sum left from here, sum diagonal from here, and sum top from here. And then what am I going to do? I am also going to update this. So this here is the number of ways of reaching our yellow element, right? I will then update for this yellow element the sum left, the sum top, and sum diagonal. For this one I'll also update the sum left, sum top, and sum diagonal, and for this one also I'll update the sum left, sum top, and sum diagonal, right? When I say update, I will update it from there. So again, just to show you all, what I'm going to do is I'm going to consider 4 properties in each cell. The first property being sum left, that is, take the sum of all of the elements on the left side, take a cumulative sum of that. Okay, so if I have to actually write this down, each cell has 4 properties, number of ways, or rather ways to reach I comma j, okay, then cumulative sum of reaching ij from left side, cumulative sum of reaching ij from top, and cumulative sum of reaching ij from diagonal. Each property has these, okay, each cell has these 4 properties. What we are going to do is we are going to say ways of reaching I comma j is the entire cumulative sum of reaching the left side. So I'll say cumulative sum of I comma j minus 1, but not just any cumulative sum left, because from j minus 1, from any of the previous columns I could have arrived here. From any of the previous columns I could have actually arrived over here, and that cumulative sum I need, because this j minus 1 stores the cumulative sum of all of the ways of reaching from the left side. So instead of going through all of those previous columns, I'm saying take a cumulative sum of that, so I don't have to calculate that again and again. Okay, then I'll say cumulative sum coming from the top, which will be I minus 1 j, plus cumulative sum coming from the diagonal, and that will be I minus 1 j minus 1, right? This is the number of ways of reaching I comma j. Now that I've reached I comma j, now what do I need to do? I need to update the number of ways of reaching, or the cumulative sum left is what I need to update, right? So what I'll say is cumulative sum left I comma j, because this cell now needs to have that property. So I'll say for cumulative sum left I comma j is equal to cumulative sum of left ij minus 1 plus ways ij, okay, plus ways ij, because now I'm going to include the number of ways there are of reaching my own cell. So what cumulative sum ij just does is the sum of the ways of reaching each one of these cells, okay, each one of these cells, the sum of reaching each one of these cells over here. And now that yellow is there, you are also including yellow's ways as well. Okay, then what we're going to do is similarly cumulative sum of reaching top of I comma j from top, that is you coming from top, you say whatever is the previous cumulative sum I minus 1 j plus ways of I comma j, and whatever is the ways of reaching from the diagonal I comma j is equal to j minus 1 plus ways I j. That's what we're going to do over here, right? So now the easier problem was if it was one step, so we would have just needed to create some sort of a recursive function like this, not a recurrence relation. That was pretty simple and straightforward. That was something like this, right? So the easier one was something like this, where I could just take the sum of the previous ways. But now I can't just take the sum of the previous ways. What I need to take is the sum of the all of the previous left elements, all of the previous diagonal elements, all of the previous top elements. So I actually have to create this cumulative sum arrays as well. Now the big question here also is we cannot pass over obstacles. So what you need to do is, if there is an obstacle somewhere, okay, if there is an obstacle previously, you do not take the cumulative sum. You stop there and you start the cumulative sum again. Or what I mean to say is, at this point, let's say, okay, let's say now you have an obstacle, let's say over here. Let's say your obstacle was over here, which means your sum left will need to have the sum of only these two elements, and which is possible to do, by the way. Because when you take the sum left here, your sum left here will be 0, because the moment you get an obstacle, you will ensure that your obstacle sum left is 0, sum top is 0, sum diagonal is 0. So then when you are calculating over here sum left, you are going to have 0 plus my own ways, right? So going forward over here, this automatically does not contain the sum from this first element, because you did not count it forward in your cumulative sum. So your cumulative sum approach actually takes into account this as well. That is, if it's an obstacle, initialize this cumulative sum I comma j. So if it's an obstacle, this j minus 1 would be 0. Cumulative sum left I comma j minus 1 will be 0. So that's your edge case condition. That is, if it's a obstacle, you're going to make sure of this, right? So yeah, I hope you were able to figure this one out. You were able to understand it. If you're not, pause it, go through it, check it again, try to understand it. We do this kind of patterns in our advanced algos data structures bootcamps, and that's exactly what we're trying to tell you, that this one is just memoizing on top of memoizing. That's all you're trying to do over here. You're just trying to take two familiar patterns and try to combine them. The solution for this will be up on the Edyst platform, so you can actually check out the code also if you want, and go ahead and try to apply it as well. And yes, keep participating in the daily challenges, where we will have more such amazing opportunities for you. The link to both this challenge as well as the Algos and Data Structures Bootcamp that we are launching are both in the description below. Also, just one last thing, please don't forget to like this video if you're liking these daily challenges. Subscribe to this channel, because we're going to release a lot of amazing such challenges going forward. And yeah, share it with your friends, and maybe they also can win some prizes. All right, all the best everybody, and I'll catch you all next time. Thank you.